Hello everyone. In this video we are going to talk about the machine learning projects pipeline. So once you come across few machine learning techniques and now you want to apply them and see how you can train a machine learning model that can be used for some real world problem, you can only do so when you are aware of the whole pipeline or the end-to-end mechanism of how a machine learning project can be implemented. So that's what we are going to discuss today in this lecture. So let me draw the different components of the pipeline and we will discuss them one by one. So the first thing that you need to be aware of is data preparation. So this is going to be the first step of the pipeline, and that means we need to be aware of the kind of data that we are using for our project. So this data might either be available in the form of a dataset, either be an already compiled dataset, or if that is not the case, so then you may also need to collect your data. For that you may be either scraping different websites like blogs, forums. You may be using some APIs of the popular web applications that are sharing their data with those APIs, so you may need to have access to them. And in some cases you may also have the data available in different databases, and your job would be to combine all that data and use it together in order to train a model. So all these components are part of the data preparation part. However, for research purposes, generally we go with the already available standard dataset, and therefore we do not need to worry too much about this part. However, for building different kind of applications, we either have to use the available datasets that are compiled already, and we may also need to make use of these techniques. So with all these techniques, we basically address a major question, that is, does the data exist? Because in the earlier lectures, we talked about the fact that machine learning models are all based on data. They get all their learning from the data, and they can only perform well when the data is good enough. So with this, we need to know where our data is going to come from. If you do not have data, machine learning model cannot be a possibility for such a problem. Then, even if we have data, there are still some questions that we need to ask ourselves, and that are, where do we get this data from? So as we said, if there are data sets available, where are they? Are they publicly available? Or do we need to get someone's permission in order to use that data? Does that data set has privacy issues, where you may need to anonymize some of the data? Or is it already being anonymized? So all these questions need to be asked in order to pick some data for your model. Then the next part, I believe, is going to be data pre-processing. In the pre-processing part, we'll call it the second part of our data. Now we have resolved that. We have got the data, it's public, the privacy issues are being resolved. We have combined data from multiple sources, so everything is ready, but the data, so we have all the data available, but the data is not in a form where it can be readily accepted by machine learning models. The data isn't in a form where it can help us get good patterns. So we need to pre-process this data and get rid of some of the problems that this data may have. So first we'll need to decide whether this data is structured. Machine learning models accept data in structured form, that is arranged in the form of a grid with rows and columns, and the values are to be numbers. So is that the case with the data that we have? If it's not, we need to convert it into such a structured form. Then this data may have noise, it may have missing values, it may have outliers or any other kind of anomalies. So we also need to get rid of that at this stage, because if this data is being passed on to train the model, all these problems are going to affect the performance of the model. So we also need to get rid of all those issues at the pre-processing stage. We may also perform some exploratory analysis just to have a feel of the kind of data that we are having. So for that, we may just plot some part of the data. Maybe if it's textual data, we may find the most significant words in the text. We may find the total number of documents. We may find the average length of each document. If the data is in the form of images, we may try different sizes of the images. So we basically try to explore our data and get an insight into the data, or try to build our understanding of the kind of data that we are dealing with. The next part is feature engineering. In this part, we deal with the problem of dimensionality reduction. Because generally we are having lots of features in the data and they may not all be very useful. For more features, we need to have much more records, and generally that is not the case. So therefore, in order to identify good patterns from within the data, we would want to reduce the number of features. And in order to do so, we would be particularly interested in getting rid of those features that are not conveying meaningful information. So if this is our grid and we have the features along the columns and the objects or instances along the rows, so we would want to remove all those columns that are holding features which may not be useful in this particular case. For example, if we are classifying good and bad students, so the eye color of the student may not be a good indicator or feature for whether the student is going to perform well or not, so we may get rid of such information. So dimensionality reduction is reducing these dimensions, reducing the data from a high dimensional space to a low dimensional space. First, to reduce the computational cost. Secondly, to come up with better patterns, because if we have fewer features and more data instances, then of course the patterns are going to be good enough. So since we cannot increase the number of objects, because whatever we got from the previous step is all the data that we have to deal with, so therefore we would try to reduce the number of features. In order to reduce dimensions, we generally perform two types of operations. There is feature selection. Feature selection is a kind of mechanism in which we look at a feature and see how useful it is for a particular activity. Just like in the example we discussed, we have to classify if these are the labels, and we have to classify good and bad students. So the eye color, this feature was irrelevant. It was evenly distributed for all the good and bad students, so therefore we got rid of it. Or maybe due to domain knowledge, we know that eye color has nothing to do with the student being good or bad, so we got rid of this feature. So whatever the case, removing or not using some of the features from the feature set is the process of feature selection. There are statistical methods that helps us to identify which features are more helpful in predicting the label as compared to others, and we can make use of them in the feature selection process. So if we have, let's say, 10 features initially from 1 to 10, and after a feature selection mechanism we have reduced it to 3, so now it means we are going with this smaller feature space and we are going to learn better features, because all the features that were irrelevant are being removed. So we are going to evaluate each feature and see if it is good enough to be used for training the model, and the process is going to be repeated for all the features. So in feature selection we make the decision whether to use a feature or not to use it. The other type of approach for dimensionality reduction is what we call feature extraction, or it's also called feature projection. In this case, instead of either picking a feature or not picking a feature, we project multiple features and represent them as one feature in our problem. So basically, representing multiple features as one has the impact or the effect of all those features contributing in a single value. So now a question is where to use feature selection and where to use feature extraction. So if we have the information among features that is not evenly distributed, for example, this feature is very helpful in deciding whether a student is good or bad. This feature is also very helpful. The third feature is moderately helpful, and all these features have very little support in identifying the label. So let's say the first feature has 40% of the information, the second has 35% of the information, and the third has 22% of the information. So that makes it a total of 97% of the information available in just these three features, while all the remaining features have 3% of information. So in that case, feature selection is going to be a good strategy because we have uneven distribution of information among these features. Some features are very helpful while others are hardly any good. So we can just pick the features that are helpful, and just by losing 3% of information that is not going to affect us a lot, we can reduce the number of features from 10 to 3. In case of feature extraction, if we again have all these features, but in this case all the features are almost equally important. For example, this feature has got 5% of information about the label, the next one has got 6%, then this one has got 10%, then 5%, 2%. So the same way, although if we perform feature selection, we may pick the ones with higher values, but that still is not going to give us too much information because the information is almost evenly distributed. For example, again, if we pick 3 features out of the 10, in this case, we may only retain 40 or 50% of the information because the information is so evenly distributed among all these features. So in that case, feature selection may not be a good strategy, and therefore we would perform the feature extraction techniques in order to combine these features and represent them as one. So we may combine some of these features as one and then make this the second feature and then this the third one. So although we haven't ignored any of the features, but we have combined the effect of multiple features into one feature, and now we can train our model on these 3 features, F1, F2, and F3, which are the extracted or the projected features, and we can train our model on this case. So high contrast among features, use feature selection. Low contrast among features, use feature extraction. An important thing to remember over here is that there are techniques like neural networks where feature engineering may not be of much importance as it takes care of all the features by itself. So there are machine learning techniques where feature engineering may not be a big concern to us. Next is model selection. So we have different types of models available in machine learning, and therefore it's practically impossible to try all these models on the given problem, but we have some heuristics that we can use in order to decide which model to pick for any given problem. For example, if we are interested in deep neural networks and we are dealing with images, then convolutional neural networks may be a good choice. Which exact architecture of convolutional neural network, that we have to tune with respect to our problem, but instead of trying all possibilities, we have restricted our choice to convolutional neural network, and now we can explore and try different architectures within that space. The same way, if we are dealing with text and we are tackling a problem of sequence data, then RNNs and LSTMs may be a good choice. So that's how we have a choice of models, and therefore we may first study the architecture to pick a type of model that is frequently used with such problems, and then we may select a model that we are going to use for this particular problem. So once we have selected our model also, the 5th step is going to be fitting or training the model. So in the 4th module, we selected a model, and now we are going to try different architectures retune the hyperparameters of the model. Try different settings and see how the model can be trained well. We want the model to have better understanding of the problem that we have. So we would keep on changing the hyperparameters in order to tune with respect to the problem that we are having. So this is particularly important as the model gets attuned with the data as much as possible. Generally, if we could achieve overfitting, it would be better for having a complex model that understands the training data very well, and then we can regularize it and generalize it to perform well for the test case. So this may be a good approach for tuning the hyperparameters. First, keep on increasing the complexity of the model in order to achieve overfitting, and then once you have overfitted the model, then reverse back, generalize it slightly so that it can perform well on the testing data also. If you do not overfit, you may not know what level of complexity is being required for this particular problem. There may be multiple loops in this approach which I'm skipping for now, so the same for this module also. You may have to keep on tuning these hyperparameters and retrain the model and see how good it gets, and then again change your parameters and repeat the process. So there are going to be lots of repetition in this step also. And then the final step is going to be, or the final module is going to be, the evaluation. Now we want to test if the model is ready so that it can be used for the real world problem for which we were training this model. So for that case, we first need to identify our evaluation metrics. We have different types of demands based on the kind of problem on which we are applying our model. In some cases, reliability may be of most importance to us. In others, accuracy and efficiency may be very much important. So based on the kind of problem that we are dealing in, the kind of real world environment in which this model is going to be deployed, we need to come up with evaluation metrics so that we can evaluate the model according to its purpose. And then we need to decide for the experiments, there is the train and test split, the validation techniques that we are going to use for the experiments, and evaluate our model and see how good it is doing, and then may go back to step 5 and see if we could improve the evaluation and stay with this problem for a while to see how it can be improved further. So with this, we are going to get a trained model that is good enough and that can be used for any real world problem. Finally, we are going to have a 7th step or module that may not be needed in the first attempt, but this is about retraining your model. So this model that is trained on this particular data using this approach may not be useful down the line. So you may need to retrain your model and think about all these processes again, or maybe something else, in order to decide how you can keep on improving this model so that it can tackle the issues that may arise in future. A model that is trained on a specific type of data for a problem may not be useful for the same problem maybe few months down the line, because the data keeps on changing, the nature of the problem keeps on changing, and therefore the model also needs to stay abreast with all those changing requirements. So that was a general idea of the pipeline of machine learning and how it can be used for different kind of projects. Thank you. And one more point that we generally skip in academia or in research projects, where if we have attained high level of accuracy, the job seems to be done. However, at production level, there is another concern that now this model that has performed well with laboratory setting in offline arrangement, we need to deploy this model on some server and make it available to general public or for whatever the service it's being produced. So in that case, the choice of hardware where the model is going to be deployed, retraining and re-evaluating the model in real world setup. The decision on the different cloud services that are available out there and how to make use of them are also going to be of a concern, considering the performance that a user may get and the business value out of this product. The front end of this model, or how people are going to interact with it, that is it going to be a web-based application or some mobile app, are all concerns that are related to the real world use of this model and the business value associated with it.